Let's go to the bathroom.
Yeah.
Gravity.
Okay. So, finally we're ready to begin lesson 9.
Woo!
Yeah.
Am I the only one excited?
No.
That was the lead up to 9.
That was like this lesson in itself.
How can acceleration due to gravity be calculated?
How can the acceleration due to gravity be calculated for different planets? We know what the acceleration due to gravity is on the surface of the Earth. Tiki, what is that acceleration due to gravity on the surface of the Earth? All objects, regardless of mass, when air resistance is not a factor, when dropped, accelerate at what rate? What is the acceleration due to gravity on the surface of the Earth? Yeah. Say that again? Either or. 9.81 meters per second squared. That is the acceleration due to gravity on the surface of this great planet we live on. But it's not 9.81 meters per second squared if you went up a little bit higher above the surface of the ground. And it's not 9.81 meters per second squared if you were on a different planet. So the question is, how can this acceleration be calculated? So to answer that question, we're going to consider this scenario here, where you have a central mass, m1, and you have a second mass, m2, orbiting the first mass.
Mr. Kessler.
About this close, my man. Couldn't hear. I couldn't read it. There needs to be a DVD-R.
Oh, you can't open a PowerPoint?
Oh, the PowerPoint, not the film?
Yeah, the PowerPoint.
PowerPoint.
Yeah, it's just a PowerPoint. For example, throw it on.
To go for the morning commercial.
Yeah, can you guys put a
I don't know
PowerPoint?
if he can.
I heard that.
You were meant to. This is very confusing.
Now, Julian might be pretty confused right now.
Okay, so there's
I went to that thing.
right here.
Okay. It looks like a diagram.
Okay, so that's what like PowerPoint looks like.
Right.
And then if you hit slideshow and play from the beginning, and let me close this other thing out here.
What was the other thing?
Okay, so here you just press this. I don't have the sound hooked up to the speaker, but
Why isn't it hooked up to the speaker?
because I have my laptop.
No, don't go crazy. I don't care. Oh, that's so much better.
A student made this,
I believe you.
and I don't know how to put it from.
Okay.
So
Let's see if he can do it.
yeah, if you
If
can't,
he can't, no one's going to know that it's Pizza Love Pizza Day.
well then
Which is
we'll
one of my favorite days.
we'll switch things around.
Mr. Kessler, have you lost weight?
No, I'm a finder of lost weight. It was Thanksgiving, the perfect holiday.
Thank you.
Bye. Thank you. Sorry I interrupted.
No problem. Julian, just ignore that.
Gesner.
Hi, Julian.
Okay, so Simon's table partner.
Simon, wake up.
He's with us in spirit.
Yes. He's actually in his bed right now, sleeping.
Okay, so you see that force right there? There's 3 different expressions you could write down for that force. That's right, not 1, not 2, but 3 different expressions you could write down for that force. Took a snapshot picture of the PowerPoint slide so I could write on it. What actually is the physical force that's really pulling in on M2? If you want, you can think of M1 as Mother Earth. You can think of M2 as the moon orbiting the Earth. What is the force pulling in on M2? Say it loud, say it proud, Simon. The force of gravity. I'd prefer you not just say gravity, because there's acceleration due to gravity, little g, and then there's the force due to gravity, F sub g. So let's try to distinguish between those two. So here, this force right there is F sub g. And we know how to calculate that. That's big G, 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared, times M1 times M2 all over R squared. But we also learned another formula for F sub g. Remember this? Fg just equals the mass times the acceleration due to gravity. Fg equals mg. Yes? Now this is the mass that's actually out there. So this is m2. That same force is also the centripetal force. So we could say that that force is equal to F sub c, which is equal to m2, the mass that's actually out there going in the circular path, times v squared over r. So we have 3 different formulas for calculating that inward force, that F. Since those 3 forces are one in the same, guess what we could do with the 3 expressions on the right side of the equation?
Hey, don't spoil it.
David? Yeah, we could set them equal to each other.
Give it to a freshman.
Depending on what the givens are, you can set any 2 right-hand sides equal to each other. For example, if I set this formula here and this formula here equal to each other, I get m2g equals big G, 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared, times m1 times m2 all over r squared. And then, yes, I immediately notice the m2's cancel out. Yahoo! Chippaloo! So what am I left with? G equals big G m1 times, whoa, no times m2. Scribble that out of there. m1 all over r squared. So if I want to know, hey, the acceleration due to gravity down here is 9.81 meters per second squared, but what's the acceleration due to gravity way up here? Not a problem. If I know the mass of the planet down here, if I know how far away that orbiting object is from the center of the Earth, the acceleration due to gravity up there equals big G m1 over r squared. Some people like to memorize that formula. Yes? I myself, I just remember these formulas over here, and I just know that I could whip that formula up by setting any two right-hand sides equal to each other. Now, the original question was, how can the acceleration due to gravity be calculated for different planets? Basically, like on the surface. So what I'm going to ask you to do is look at this here, work with your table partner, and we just figured out that up here at this point right here, the acceleration due to gravity due to m1 equals big G times m1 over r squared. If I let capital R represent the radius of m1, the mother planet, capital R is the radius, I want you and your table partner to come up with an expression for the acceleration due to gravity on the surface of m1, right here. What is the acceleration due to gravity on the surface of that planet? We know how to calculate it up there where m2 is, no problem. What if we want to calculate the acceleration due to gravity right on the surface of the planet? If you have it, write it down, call me over, I'll give you thumbs up, thumbs down. Oh, the physics. Do we have an answer? Not sure what you're doing there. That's how you calculate it. Way up there. What about at the surface? Folks, check this out. If you want to find the acceleration due to gravity on the surface of the planet, yes? Look at this R right here. Yes? Basically, lowercase r from the center of m1 to the center of the path of m2, what is that lowercase r going to do? Yeah, that lowercase r just gets smaller. It just comes in. So we just want to know what the G is at this particular lowercase r. But this particular lowercase r from here to here, what is that? That's big R. Yes? So if you want to get the acceleration due to gravity right at the surface, what will be the expression, JD, who immediately wrote this down? The acceleration due to gravity on the surface of a planet, m1, can be calculated by big G times m1 over r squared.
I wrote it that I used little r.
That's wrong.
In this diagram, little r represents from here to here. So you would have to make a little side note. Let little r equal capital R. Capital R That'll be the radius of the planet. So if you want to know, hey, what is the acceleration due to gravity way out here where the moon is, use this expression here and use this distance here, r. But if you want to know the acceleration due to gravity on the surface of the planet, use this equation here and use the radius of the planet from here to here. Let's take a look at some examples. Take a 2 o'clock stretch, and then when you sit down, I want you to pick out a planet and calculate the acceleration due to gravity on its surface.
I choose Earth. This is an excellent.
I'm going to do it for Earth.
How low can you go? I can go pretty low. David, do the warrior.
At the bottom of the Grand Canyon, the acceleration due to gravity is greater than 9.81 meters per second squared. On the top of Mount Everest, the acceleration due to gravity is less than 9.81. Bart?
Hey. Hey, what is this?
Standard 2 o'clock actually.
Yes. Pick a planet. Pick a planet and calculate the acceleration due to gravity on that particular planet. Call me over when you have your calculation. You want to find the acceleration due to gravity on the surface of the moon? Pick the moon.
Please don't tell me that pseudo-solved also. Pseudo better not be.
I'm looking 9.81. Oh, wait, I used planes. No.
Oh, why?
The bonus planes just putting me on space. Yeah, why is that?
You want to kind of let's do Venus. Or actually, no, let's do. Oh, I know. Rajiv. Let's do. Let's do Venus. No, let's do.
There we go. I can't see everything else in Uranus.
I'd like to go to Uranus.
Funny.
Yo, great. R equals 25.
You know, I'm still
I want to go. The mass experience. Oh, 6 times 6 is 26.
Hey, Krista. I'm your good friend.
Think of the formula F equals NA.
Krista, how's it going?
M is what?
Hey, Krista.
M. A.
How's it going? Hey. Are you having any trouble in the sleep? Hey.
Yeah, that sounds great. I think my value's slightly off then. You got your values?
No.
Yeah. Yeah.
I worked out a couple of them. I think the first one I did is Earth, folks. So, near the surface of the Earth, if you drop an object, it accelerates downward at 9.81 meters per second squared. Now, Roger actually calculated with their values, and what did it come out to, Roger?
9.79 meters.
So close enough.
Yeah, not really.
Okay. Now, what about on Mars? Do you think the acceleration due to gravity is greater or less than 9.81? Anyone calculate Mars?
Equal to.
JD, you did? 3.71. Let's see what I got. I got 3.77. I'm not sure where I got my values. But on Mars, the acceleration due to gravity is actually less than it is on Earth. So on Mars, you would weigh less than half of what you would weigh on Earth. What about Jupiter? Anyone calculate Jupiter? Giselle, what'd you get? 24.7. Okay. Let's see what I got. Whoa! Oh, I forgot. Jupiter's not a solid surface. So the object will just go right in. Whoa!
So, like, what's exerting the gravity?
Huh?
What's the center?
Yes, it is. You're the only one that's not right.
It's the mass as a whole pulling it down.
So when you get to the center,
Acceleration would be zero.
Gutter for about 5
You have equal mass all the way around you. So, now that you have a handy-dandy formula for calculating the acceleration due to gravity, you have two choices. One, memorize it. G equals big G m1 over r squared. Or you can do what I do, and you can remember that if you have an object that's orbiting another one, that force has three different expressions. It's Fg equals G m1 m2 over r squared. Fg equals m2 times lowercase g, and Fc equals mv squared over r. Now, solving for the acceleration due to gravity, baby g, that's one thing you can get. But you know what? You can also get the tangential velocity. You could solve for v. So that's the second part of lesson 9.
Oh, there's more.
How can the just right tangential velocity, called the orbital velocity, of a satellite be calculated? Remember we talked about the moon having that just right velocity. Wouldn't you love to be able to calculate that? I know. Well, now, you'll be able to.
After you buy this product. Julian, stop pulling on me.
Julian, stop eating popcorn and know what you're doing.
I can feel the force of gravity from here.
That's how you're going to take a nap. They watch this video and wake up and have no idea what's going on.
Stop. Quit that.
That's what happens when I'm
Quit that.
I never know what's going on.
Farther away.
Start doing my homework.
velocity formula memorized, I always just start off with this, and I remember the three expressions, because you have to know those three anyway, for describing that inward force acting on M2. I know that that force right there is Fg, which is big G M1 times M2 all over R squared, where R goes from there to there. I know it's also Fg equals M2G. And I also know it's Fc equals M2 V squared over R. Now, if I want to solve for the just right tangential velocity, this velocity right here, which formula am I definitely going to have to use? The first, second, or third one?
Third.
Jeremy?
That was third.
The third. Definitely, because that's the only one that has that velocity in it. And tell you the truth, depending on the givens, sometimes I'll set that equal to the second formula. Sometimes I'll set that equal to the first formula. What's most useful is usually the information given for the top formula. But nonetheless, if you set those two equal to each other, what do you end up getting? Big G. Actually, and give me 1 second. M2 V squared over R equals big G M1 M2 all over R squared. And notice, once again, what's going to cancel out? M2. And you see this R over here? That's going to cross out one of these R's over there. So, that tangential velocity is going to equal the square root of big G times M1 all over R. So now we know how to calculate that just right tangential velocity. That'll keep the object going in orbit. Throw a little bit faster, it'll probably go in an elliptical path. Throw a little bit slower, it'll probably crash down to the inner planet. Throw way faster, it'll escape. So, the bottom line is, we derived two new formulas for today.
What is the escape velocity?
That's how fast you have to throw it.
No, I mean, what's the formula?
We have to learn about conservation of energy before we can learn that formula.
Darn.